Good evening, everyone. Please, anyone confirm am I audible?
Yes, sir, you're audible.
Okay, thank you.
Yes, sir. You are audible, sir.
So, how was the quiz? I mean, on the base, what difficult, easy, moderate?
Uh, it's a great, sir. Like that, all the mock questions help a lot in a quiz. I think that it's a copy of the mock only.
Yeah, in terms of number of questions, time for the quiz, all
Yes, sir.
is
Sir,
Yes, sir.
but the
Sufficient
one
time.
question is painful, sir. If I want to discuss with you, wait,
we
sir.
can, what we can do. We can release the answers of, I mean, the solutions of the quiz. Then
Okay,
you can cross check your answer, and then if you have any doubt and you feel any answer is wrong, you can put on the discourse. There we can cross
oh,
check and then talk
okay,
about.
sir. Okay, sir.
Okay.
Yes, sir.
So as I was listening to you that you were discussing before the starting of the session, so I can expect that good mark for the quiz, right? I mean that was easy than mock.
It was interesting, but this statements of true or false was bit. We are not sure. Other things are very interesting, and time was, in fact, we had a little more time also to
Okay.
check the answers. Yeah, it was good. Actually.
Yes, sir.
Respected instructor, I have a one question like that. Sir, like if we reading any kind of the equation, so
Friends, you are not audible to me at all. Lots of noise from your side.
okay, sir. Sir, now I'm audible, sir. Hello.
Yeah, you are audible now.
Yes, sir. So the thing is that like if whenever we are just watching a lecture and at some point whenever we see the equation,
Hmm?
so at some point we will like the blank, completely zero. So how deal with this? And the second thing, like that, my approach of however I studied and I watched your all the live sessions, sir.
Hmm?
So the thing is that how we visualize the equation, sir. Like that, whenever I ask a doubt any of my senior person,
Hmm?
so whatever they just they make the diagram and they will be show how the things is working behind the equation. So how we approach that type of method, sir.
So, what equations you are talking about? What formulas you are talking about? Like eigenvectors, eigenequations, something
like
like that?
like especially sir the like I understand the whole kernel function using the graph like that
Hmm?
and I watched the PCA session also. It's a very helpful, sir. It means it give a curve like the curves of the MLT. So
Hmm?
it's very so I want to learn like this, sir. So the thing is how I visualize whenever I just because I felt one question in the quiz also.
Hmm?
So in quiz also I am unable to visualize, and that was the typical question. I will mention in you in a discourse also, sir. I will post that question after this live session.
Okay, okay, we'll see, we'll check that. Uh,
Yes, sir.
so I didn't get your point up by visualizing the question. I mean, you are not able to understand what concept.
Yes, sir. Yes, sir. Whenever I see the new kind of the equation, like the Professor Rajkumar also telling that, like he was writing that equation, and at some point he get a pause
Hmm?
and explain this will be happen, and the PC will be like the thing will be changed around like this. At that time, I feel just completely blank. Like if he was saying that we have to just maximize the likelihood. So what kind of the graph will be shown? Because like the equation is it's very painful, sir, to directly deal with this. But the concept map and that the diagram will be help a lot in MLT. So like it gives us some kind of the relief. Yeah, ऐसा कुछ हो रहा है.
Okay, okay, got the point. But yeah, so it may be the case that you are not able to understand the concept pretty well. I mean that you mentioned about the maximum likelihood, the graph of those. So what do you mean by the graph of maximum likelihood? That is not something can be visualized, right? Or so conceptually you should be more focused on what's actually that maximum likelihood means. Why we maximize the likelihood and what likelihood actually gives, right? So if those concepts are clear to your head, then things looks easy. Otherwise, everything goes messed up. So that kinds of concept you should be clear with, right? And it comes with practice. You do yourself, write your equations and try or answer questions yourself what likelihood is and why we try to maximize it and something like that. That's the only way to study, right? And this kind of, if you question yourself what's actually going on, how it's working, then only you will come to know that you will feel better and you will start solving those questions. You will find those questions easy. Otherwise, everything will be messed up. Okay, we can
Yes,
talk about these questions later on after the, I mean,
yes, sir. Yes, sir. After
So,
after this live session, I mean,
hi sir,
let
good
us start
evening.
our main.
I just want to give one feedback. Okay, not about the exam. Okay, so like
mm,
we have covered like till week 4, we have covered everything. Okay, and fortunately, when we had the last, I mean, the revision session, right? So the I think you when you're discussing all the weeks all together, I was
mm,
easily correlate all the chapters actually, all the week concept
okay,
in one
yeah,
shot. Okay, fine,
mm,
they are related to each other. So what
mm,
I'm saying, sir, from going week 5 onwards, okay, I
mm,
just my what I felt like, we don't, while discussing right in the lectures also. Okay, so when we explaining about the theory, okay, you deriving formula and something like projection, everything we are discussing here, same thing happening in your class also. What I request, like, can you, while discussing any theory, can you just
mm,
take a brief small example,
mm,
okay, example at the time only, that time only, okay,
okay.
and explain the theory also along with that thing. So that
Yes,
would be really, otherwise, sir,
I
it just remain like a only theory part, okay, WTX and like that.
Okay, okay, got
Entire
the,
yes,
yeah, I
sir.
got
formula
the
based.
point. I got the point. And such feedback we got from the last term as well. I
Yeah,
mean,
Yes,
because
sir.
sir, I
sometimes
see.
notations makes
Yeah,
things unclear. I mean,
yeah.
vector,
See,
what's going on
Arun
sometimes.
Yes,
sir
sir.
was explaining, sir, so nicely, sir. Okay, but
Yes,
by the
sir.
time we complete the video, we forget the concept, sir. We don't know how to use that formula.
Yes, sir.
Okay, yeah.
Uh,
So when you're
Harish,
discussing a formula, I'm not talking about Arun sir because he cannot do right now. Okay,
Mm,
but when you are explaining the session, okay, going through a formula, just bring a small example. Okay,
okay.
so we can relate those things. We can implement those things in actually in real time, sir, and we can relate also. You can say, okay, yeah, that's how. If you, that's my suggestion. You can just ask other people like that.
Ye-
That's what
Yeah,
I
yes,
felt.
I got your point.
Lack of
yes.
real examples, sir,
I am with
they make
Harish
us a
Shankar, sir.
really problem, sir.
It's from my side also, sir. Because if you give the just a small example, na, the concept 80 to 95% of concept clear at that time. Because after that the session we just forget again. Okay, how this thing happen and what's the main aim of that equation, like that. What this process, why we chosen this equation, why we applying all that story. So that's the thing, sir.
Yeah, I got your point. You actually want to put some numbers rather than vector itself. Sometimes that creates problem, right? They create confusion. Like, okay, we'll try if we can come up with some small examples that can explain those questions and that
Thank you, sir.
equations. Yeah. So now let's stick whatever I have planned for week 5. From week 6 onward, I will try if I can come up with some small examples for those. Okay. So should we start for week 5?
Sir. Yes, sir.
Yeah, for quiz we can have a separate session, or even we are planning to release the solutions. You can cross check the solutions with that, and then after you can even you can put your, okay. So I think this should start now. Answers are released. I mean the solutions will try to release. Yes, such questions we solve, right? Such questions we solve in the mock and even with the big three session as well, right? Where we assign some scores and we'll check. We'll discuss this later. Let me start with big five. We have time. After that, we can discuss those questions. Okay. So, okay. So let me share my screen. Okay. Is my screen visible?
Yes,
Yes.
sir.
Okay. So now we are into week 5, and up to week 4, we have seen unsupervised learning algorithm, right? Where we don't have the label associated with the example. So we try to represent our data set we try to understand our data set in a vector manner. Like we try to represent our data set using some different directions in PCAs, where we try to capture most of the information using those directions, right? So dimensionality reduction is one of those technique. PC is one of those, the dimensionality reduction technique, and then we try to group those data set into different clusters, and then and in B4 we see some of the estimation techniques, right? Where we try to find out the distributions, and given the distribution, what are the possible parameters for that distribution. Such things we have seen. So there, up to week 4, we have seen some unsupervised learning algorithm. Now in week 5 onwards, we will see supervised learning algorithm. And, so this is where we start with supervised learning algorithm. So what I mean by supervised learning algorithm? In supervised learning algorithm, each and every data set have some label associated with it, with with it, right? And we try and our goal is to design an algorithm such that we can use that algorithm to predict the labels for an unseen data. Okay, so that is our goal in supervised learning algorithms. Okay, so in broadly,
What did you say, sir? Our goal is to
predict the outcomes of a unseen data
Yeah,
point.
okay.
Okay, so there are two standard tasks in machine learning supervised learning algorithm. One is called regression, and another is classifications, right? So whenever label is real numbers, and then it is called regression problem, and whenever the labels or the labels are classes, different groups, then we call those as a classification problem. For example, if we are trying to predict the house prices given some features, then that problem is a regression problem, because we are predicting house prices and the prices are real numbers. So that goes into regression problem. Or on the other side, if we try to predict whether a given mail is spam or not spam, then we have classes, right? Two labels, spam and non-spam. So such kind of problem goes into classification problem. Okay. So in week 5, will deal with the regression problem, and going onwards in week 7 or after that, we will deal with the week classification problem as well. Okay, so the idea is clear. We have regression problem. So regressions means you have data set. So setup is same here. We are assuming X is a data matrix of shape D cross N, and the by is a label vector of shape n cross 1. It means it's a column vector. So here each entry denotes the label associated with the each n example. So ith entry in label vector by gonna be
Sir,
the label.
can you explain level vector, please?
Yeah, that's I'm explaining here. So here it's a column vector where each ith entry actually denoting the label associated with that ith example. For example, to consider an easy example, your task is to predict the house price. That is a very standard common example. And you have some features. Features like, let's say the area. Area is one of the features. Let's call that F1. Some locality where your that house is present. That can also to affect your price, right? And some other features like how many BHK it is. Some three features we have been given, and given those features, you have to predict the buy, right? Predict the price. So such here you have three features. So all, let's say one data points where you have been given the area is in square feet. Let's say 45 into 45 square feet. You have been given some area of that house, and locality is present in the city. It can be categorical variable. Here it is a numerical feature, categorical feature, and the 3 BHK it is something like that. So you have been given a data point. This is your data points, and now you have to predict price has been given to you. So this is how your data points look like. So in the by column, you have been given those prices with the given example. You have been given n training examples, and those are stored in the matrix X. So X gonna be your D cross N matrix. It means that each and every example is here. Each column is one example. So this is your X1, this is your X2, up to you have been given n such examples, right? And what is those examples? If I talk about X1, so X1 is this vector, column vector. Here the area is given, and here the locality is given. Here is the BHK is given, something like that. So this column vector is one example. Such n examples are given to you, and those are stored in matrix X. So this is gonna be your D cross N matrix, right? So and those labels will be corresponding labels will be stored in the column vector. So by 1 to up to by n. It means that by 1 is the price of the first house. By n is the price of the nth house, right? So each xi,
Price is the level vector.
sorry, by is the
Price,
level vector.
n number of prices are the level vectors.
Yes, yes.
It's a column vector where each you have been given n entries, right? And each entry denotes the price of a house.
Okay.
Okay, so here each exercise is in this particular case is coming from R3, right? So in general, each exercise are coming from D-dimensional space. It means D features are given to you. Okay, so this is the setup. And what is our goal in this case? This is a regression problem, right? Because each by I is a real number here. It means that it's a regression problem, right? So this is the setup. Now our goal is to you have to design a function such that that functions whenever if a data point is passed to that function, it gives the prediction, right? Or you can think as a black box. Whenever if data points is passed to this point, let's say and any data points passed to this, it gives me the predictions for that by head. Okay, this is the outcome of prediction. So this is our task. We have to peep into this box now. We have to design such box, or we have to design such function. Whenever we give some input to that function, it will give me the predictions, right? This is our goal. Okay, so what I mean by function is just a mathematical function. Where, it's RD to R. It means when a d-dimensional data point pass to this function, and it gives me the output, right? So we have to design such function. This is our goal. And in machine learning terminologies, we call this function as a model. Okay, so model is nothing but a mathematical function that we have to learn. Learning means we have to come up such function. There are so many functions, we have to come up one function for that, right? And in machine learning, we call those function as a model. Okay, till this point, any doubt?
Sir, I have one little doubt, sir.
Yeah.
Shall you show the example, a precise example for a label vector, and that another one is a label vector and another one is a feature matrix, sir.
Yeah, feature matrix. Right.
Yes, sir. Yes, sir.
Hmm.
Like you show that the x1 is equal to that 1 BHK. So, sir, this is the feature matrix, sir, or label vector, sir?
This is one example which is coming from d-dimensional. When it means it takes some feature values, d features
Okay,
value.
sir. Okay, sir. It means it can take any number of features, so it will be the fixed feature, and n d is representing the number of that
Number of features. Number of
dimensions,
features.
and n represents the number of the vector. Like that, how
Number
many
n
vectors?
represents number of examples in the training data.
Okay, number of examples. And sir, what is the sir why label vector? So, give example of the label vector like that BHK, sir.
No. It's a price here. In this case, by is a
Okay,
label.
okay.
It's a label that associated with that example.
Okay, sir. Now it's clear, sir. Okay, sir, you can continue, sir. Thank you.
Sir, may I ask?
Yes, sure.
Hello.
Yeah, please.
Sir, my doubt has a link with the content which has been given in 5.4, but that has a direct relation with here. Like as you said rightly, that we say, for example, we have three features, right?
Hmm?
And starting from unsupervised learning, our understanding has been that all the features put together form a vector, correct?
All the features are.
All the features put together, say for example a data point, ith data point, right? So all the three features put together form a vector, correct?
Yes. Yeah.
In lecture 5.4, when professor is talking about height and weight,
Hmm.
so what he is saying, say for example three data points are there, x1, x2, x3.
Yeah, we will come to that example. That particular
Okay,
example will
okay,
come.
that has no correlation with this, right?
Yeah. We will come to that. I
Okay,
got
that's
your
fine.
point. What you are talking about, I
Yeah,
will come.
that's fine. That's why I asked at the beginning
So
itself.
till
Thank you,
this
sir.
point, what is our
Yeah,
goal? That is
crystal
clear.
clear,
That is
crystal
complete. The
clear.
setup of a regression problem is clear, right? And
Yeah,
what
yeah,
is our
clear.
goal?
Yeah, clear,
Okay.
clear.
So you have been given an example which are coming from the d-dimensional space, and now you have to come up with a function which actually we give the predictions, right? So how good our prediction is, how better the performance is of a model, how to quantify that. We need to quantify those as well, because you can come up with any function. Out of those functions, you have to choose one function, right? How to choose those functions? So you should have some measure that can quantify the performance of the model. Okay, so what do you think would be a better performance measure that you can use in a regression problem?
Sir, what is weight vector?
Yeah, we'll talk about this. We'll come to that. Okay, so let's say you have been given a model. Now you have
What is
to
question, sir?
you have been given a model. You have been given a function that predicts the output, right? Now, how you will measure that output is good or your model is good or not?
Like
How you will
errors
measure
should
that?
be less. The price.
Yeah,
Yeah,
error,
price
right? The
price
error.
should match with exact price.
not exactly it should match, but it should be
Correct.
closer
That
to
is
the
the
actual
ideal
price,
condition.
right?
I said, yeah, yeah, correct. Errors should be minimized.
Yeah.
Yeah.
Yeah, so check the how good our model is or how it performs. We need some measure, and that measure in the regression problem we define as a error. So error is defined as the prediction value, whatever is predicted, and the actual labels of that. So we have access to data set. We predict using the model by head. We are calling it, and the actual label of that. Let's say for the ith example, this is the error associated with the ith example, right? And if we sum over those errors, let's call sum over those errors, we will get the total error, right? Can I use this as a measure to check the performance of the model? Can I use this as a measure? Sum of all the errors.
No, sir.
Why not?
So because there will be negative quantities and they may cancel out each other.
Yeah, because of the positive and negative quantities, it may be case for some of the example the prediction is higher. In this case this will be positive, and for some of the example prediction is lesser than the actual, and in that case the error will be negative, and that will cancel out, and that will deceive our performance of the model. That's why we are not choosing this. One better way to choose the total loss or total error is the just square of those errors and then sum over all the data points. So this will be my by hat I minus pi I square sum over all those points, right? So this is called square laws, and we use this square laws as to measure the performance of the model. We can even choose the absolute error as well. That is actually we take the absolute values.
So cannot understand the second step.
This step.
Why?
So,
Yes.
so this is the error associated with any example, with the ith example, right? And we have n example. So if we square those and sum over all such examples, then we will get the total loss of the total loss for the training example.
All the predicted value. First I sum up, then I subtract all the actual value.
Yeah, this is the prediction value and this is the actual value. So this will be the error with the ith example. We'll take for all n examples the squared error of those, right?
Uh, sir, I have one question, sir. So, like that, you already told that you have the square loss function now, and you have the absolute function. So, sir, why we didn't use the absolute function lot, like that the square loss function?
Yeah,
I
so
mean, which is the
mostly,
better, sir,
yeah,
from the
absolute. So absolute loss.
optimization.
Yes, so absolute loss is not a good mathematical function just because it's not differentiable function. We will see how the differentiability come into the picture for when we try the function. Can you please mute yourself? There's lots of noise here. Yes. Okay. And in the last, when we'll talk about the probabilistic view of this model, we'll see that square law is a better choice than the absolute law.
Sir, just quick 5 seconds, sir.
Yeah.
So I know on squaring it doesn't make sense, but before squaring, whether it's a predicted minus actual or actual minus predicted.
Here, you can choose any of these. It doesn't matter.
No,
At
I
the
know
last,
after squaring it doesn't matter. That is clear. But
but we don't use this as a measure. It's not a measure. It's not a
okay,
good measure,
that's fine. That's fine. Okay.
right? It's not a good measure.
Sir, actually, I have a doubt, sir.
Hmm?
Like in MLF, we are using 1 by n formula, no, sir? Like for this, we have to
Yeah.
use.
It's total sum of square. We can even take average of that.
That is means some.
Yeah. Okay, it's just a constant, right? If both sum of square error or the mean of square error, both can bugs equally better in any model, in a regression model. Okay, we generally goes for the mean of square error. So 1 by n take the mean of the square error, right?
Yes. Okay, sir.
So this is our loss now. So we will stick with the squared loss. So in our case, to check the measure of the model, check the performance of the model, we use the measure square mean of square error. Or sum of square error, both will work better. Okay, square loss.
So any reason why we are using square error? Why not absolute error?
Yeah. So one reason is that it's not differentiable function, and we'll see that differentiability come into picture in the case of regression model. When we try to find out those functions, and another reason is that we'll discuss later in this section. When we will discuss the probabilistic view of this model, where we see that square loss is actually a better choice than the absolute loss. Okay.
One more,
But
sir. Yeah.
the apps, sorry, sir, what question? The absolute error function will not be, it is differentiable, right? But it's easier to find the minima for a convex function, that I understand.
Yeah.
But because the minima is the global minima, but for this, it's not differentiable, is it? I mean,
yeah, absolute function is not differentiable at the point where it goes zero, right?
Zero,
So,
correct. It's like mod
mod
x, correct. Mod x, correct. It's not differentiable. You're right. Absolutely.
One more, sir. If you take the square error, then if the difference of the square is less than 1, then its square is again smaller.
Yeah, yes, it may happen. Of course, it may happen.
So it doesn't count the proper error. No? Suppose difference is 0.1 fractional value, and if you take the square of 0.1, then it becomes 0.01. So it reduces the error again.
No,
So
it is okay. Even for some of the points it goes high, and we are doing all such examples, so it won't affect. It won't affect the. It's actually giving some measure. It's not the actual error in the case of the how it's deviating from the actual level. But at some in aggregate we get some performance of the model, right? At the last we have some quantity that can define the performance of a model.
if you take the square of that error, then again it reduce the error. No, we will not get the actual error.
Yeah, it may happen, but it won't affect your performance, right? It won't. There's lots of noise.
From what I understand,
Ankush,
guys,
Sir, can I explain what he's asking?
Yeah, go ahead.
So basically, we are not interested in the actual absolute value, whether you square or not. We are just relatively choosing a best fit curve, irrespective of the magnitude of the value. Among two best fit curves, whichever gives the lesser value, we'll choose that.
Yeah, so the error function we've created, we never interpret that. We never look at the value and say it's a good model or a bad model, right? It's meaningless. It is just a way to obtain the best parameters. That's it.
Yeah, that is one way to look at it. Look at this, and we'll talk about this. We'll just let me go on. Okay.
Yes.
One question here. When you said differentiability, it is differentiability you're looking at because you want to see the minimum of the error, is it?
Yeah. We will try to find We will use some optimization technique, and differentiability comes into pictures there, right?
Yeah. Thank you very much.
Okay. So our task is to minimize this error, right? Given a model HW, given a model H, we are denoting the model by H. So it's a function from RD to R. Given a model, we find the loss associated with this. It can be loss, or we can call it a total error. Let's call it totally. Our task is to minimize this, right? Minimize this error. So we will choose those functions which actually giving the minimum error, right? So, can you please mute? Okay. So one such function I can think as for every training example, I can the function actually gives the real output, right? So for this function, what will be the error? Total loss.
Zero.
Zero, right? So the theory says that if we choose those functions which give me the minimum error, then it says that this function will give me the zero error, and I will end up choosing this function, right? But this function actually not a good function because it actually memorizing each and every example. And this is not our goal. Our goal is how it works on the unseen data set as well. Our goal to design a function, whenever we pass a value to it, it gives me the output. But it's actually memorizing only the training example, all those n examples, right? So this is obviously not a good choice. So what we do, we actually we restrict the model, the search space for this model to the linear functions. Okay, we choose HW from the linear models only. Linear functions of features.
Why only linear functions? Because
okay, so
you just made two statements a little earlier. A little statement, because one thing you said is it is memorizing.
Yeah,
Okay,
this function is memorizing, right?
Yeah, how do we differentiate whether it is memorized or not? Just because it is able to interpret, is that sufficient cause for me to actually say that it is memorized? Because if all the lines, all the points lie on a line, then y is equal to mx plus c, I'll always get the proper value. So how do I actually differentiate on a parabola? Let's say if all the points lie on a parabola and I get the equation of the parabola, I'm done. So I'll be able to predict what the next value is. So why is it that a statement is being made? It is memorized.
No,
In the
for
context of
this particular case,
yeah.
in
Yeah,
this example, what's happening, for every training example, I'm just predicting the actual level.
Okay.
Right? So it's actually memorizing the data points. Is nothing. It's learning nothing other than that. For any unseen data point, it will fail to make the prediction, because it's only making prediction only for those which are from the training example, on an example. If any examples which is not seen by the model, which is not in the training example, it will fail to predict the output for that particular example, right?
But that will be known only after we test it, isn't it?
No, we are not about what your model here is. Model says that for xi, the level is yi, right?
Yes.
So here xi is coming from the training example. Whenever any unseen data, I mean unseen means any data point which is not in the training example, it doesn't know what will be the output for that. This function doesn't know what is the output for that unseen data. This only knows only for those values which are seen in the training example.
We
That is
can
why
also
it
say
is
like
called
this, right?
memorized.
We can also say in the other way, like we haven't learned the data. We are just whatever
Memorize the
we are
data
giving the
point.
output. Yeah, we have. That is the point I think Sir made. We haven't learned the data and given a model. We are just giving whatever in the data set. We are giving as
Yes.
output. So this
It
is
just
not a good
memorize
model.
the thing.
Yeah, it's something like we written a program, we given a function, like we give the input, you give the output. That's a finish.
Right?
Okay.
And why we are restricting the linear function that we will talk about. Actually, we restrict our space to the polynomial functions, and actually polynomial is right. So linearly we are by restricting our space to linear functions, we are making assumption that the let's assume this is the labels and this is the first feature, only one feature, and this is the label. We are assuming that the label association between label and the features are the linear relationship. Okay, so this assumption we are making, and we will talk about the non-linear data set as well. And by now you can guess, right, what how we can deal with the non-linearity with the data set, right? Okay, so
Kernel.
yeah, kernel method. So we just transform our data set into higher space where it comes into a linear space, right? Linear association becomes linear. Okay, so by and you know that any continuous function can be interpolated using the polynomial function. If you, I don't know if you have seen this in any math courses like Taylor series expansion, where we try to interpolate any continuous function using the polynomial functions for any desired. By using some desired xc, we can even approximate with any desired precision, right? So that's why we can restrict our search space to the polynomial function, or we can restrict our the search space into the linear function. So here we are making assumption that the association between the labels and the labels and the features are the linear relationship, right? Okay. So what we are doing, we are restricting our space, search space into a linear function. So our model will look like something like that. So it's a linear function of the feature. This you can even call it as f1. So it is w f1 f1 plus w2 f2 up to wn x fn. So these are okay. So this would be d here. D. So D features there. So we are taking a linear function of the feature. So this will be our feature, and in the vector notation, it can be written as W transpose X. So here W becomes the column vector of W1 up to WT. And these are the parameters that we have to learn, right? Once we have those parameters, we have a function. We can pass any vector here, any data point here. It will give me the output, right? So W here is a D-dimensional vector here, right? So now our task is to find these W's, right? And we know that how we can find, we can use the performance here, performance measure, which is the squared loss. So this is the squared loss, this is the prediction for any higher data point, right? W transpose Xi, and this is the actual level for that point. And this is the error. This will be total, this will be the error with the ith example. square it, sum over all those examples, and our task is to minimize this error, right? And here the parameters are W's, right? So we have to find W for this error is the minimum. So this is our goal. This is the objective function.
One, please repeat the linear function.
Sorry, linear function. So
Hi,
we are assuming that our label are associated in the linear fashion to the features, right? This is our assumption, and we are saying that our model looks something like that. It's a linear in the features. So these are your features, your D features, and we are assuming the relationship between the features and the labels are this linear relationship. Now we have to find these W's, and in the vector notations we can write as W transpose X, where W is this column vector. Okay, X is your data point.
So it is each data point against which it is being done.
Yeah, for
Or-
any data point, this is your prediction.
Okay.
X is our data point and
X is W is the weight vector. This W1 up to WD, right?
how can you calculate W?
W is the weight vector. So this equation I can write as W transpose X. W is your this W1. W transpose will be this vector WD.
W
And
is given in the problem.
W we have to find out.
So is it like PCA1 and the way we do, right? W1, W2 we take out from there. So Xi is a combination of W1 X1 like that, W2 X1 like that.
No,
Analogy.
PCA is nothing to do with regression problem. PCA is actually is an unsupervised learning algorithm where we try to find out different dimensions of the features. We get rid of the actual features and we try to find out different dimensions for the data set where we can capture most of the variance of the data set, right? Here we are actually using the prediction task. Here, let's assume you have one dimensional data set, X one dimensional data set, right? X is the feature and the label is by. Right? So this is your label here, and the data set is the input space is one dimensional again, and we are assuming that the label and association between label and features are linear. So they are coming with some line, some let's say line in the 2D it gonna be line, and those will be data. So they are coming using this line, and with some associated error is associated with every data point. So this is the error, right? Now our task is to find such lines. Our task is to find a function. Let's call this by f of f dash of x, which actually is approximate to this function f of x. This is some function by equal to mx plus c, right? Or we are calling it w1 x1, w1 x plus w0. We haven't uh, introduced this terminologies, but you can assume this as a weight vector w1. So we have to find these w. Once we have this w, we have this line, right? And now we have
We
to
have
find this line.
W1 to WD, lot of W's, but in the equation there is only W1 and W2. Why?
Here we are taking only one dimensional data set. Here in this particular example, I've taken data set from R.
That means among all the W1 up to WD, we have to choose only two W's. What's
W. In this particular case, I'm to choose only W1.
W1 is plus W2 na?
No, I haven't introduced this bias term. I'll come to that. But just think any line passing through origin, we have to find one line which is passing through origin. And so this will look like something like W by equal to WX, right? This line is by equal to MX, WX. So I'm to find this W, which can
That means C is 0.
C is 0 in this particular case. I'm just assuming that a line passing through origin will be best fit, will represent our data set. So there for different W, there will be different lines, right? I'm to choose best line for this particular data set. So for choosing that, I have to use measure that square law of measure, and I will minimize this, right? For which W it is minimized?
How can I say that the line passing through origin is always the best line?
Yeah, it's not always the best line. That's why we will introduce the bias term onto that.
Sir, sir,
Yes.
here we are identifying a best fit line with the feature or with the data points across the levels. Okay. In the subsequent lecture, there we also encountered that within a data point, the features may be in linear fashion. We applied some tricks. Okay. So is there any case where there is a nonlinear equation available for data points and level?
Yeah, of course there are, and we will deal such example using kernel methods. Let's say you have been given your features is something like that by using sine curve. Okay, your data points are you coming from this equations, right? So linear, if you try to model a linear model for this, it may be something like this, or something like this, or something like this. It's not a best fit in this case because the relationship between the features and the level is not linear one. Here it's some trigonometric relationship, sine of x, right?
Okay.
But we know from the theory that any continuous function can be approximated using a polynomial function. So it may be something like x cube. If you've seen sin x can be written as x plus x cube by factorial 3, something like that, right? If you have seen somewhere here. So any continuous function can be written as a polynomial function, can be interpolated using polynomial function. So actually degree defines there at what level of precision you can approximate those. But for now it's better to know that any continuous function can be interpolated using the polynomial functions. That's why we can even search for the polynomial. Here we are only assuming that linear function, but we can even deal with the non-linear functions, non-linear data set as well. Such non-linearity can also be handled using regression methods, and we'll come to that in the last part of this session. Okay, we will introduce the kernel regression.
Okay, but kernel regression, what Sir has explained regarding that nonlinear relation in between the features, but he has not touched the nonlinear relation between the level and the data points.
No. Here we actually assume that the features are independent to each other. But in practice, it doesn't happen. But for now, you can assume that features are independent to each other or orthogonal to each other. But it doesn't
Yeah,
follow in
that's
the
correct.
practice. We know that even in the theory, it doesn't follow. But that's the assumption we make for any machine learning model.
Okay.
Okay.
Sir,
Yeah.
I have a question, sir. I have a
Hmm.
question. Like, is there any line that doesn't pass through origin, sir? Can you give an example from real life? Like,
Okay. So next we will introduce this thing. So first let me vectorize this thing. So this is our task. You have to minimize this loss, and this is I can even write as a vector notation and vector notation. Okay, so W transpose. I'm summing over those. So X is your data matrix, G cross N matrix. If I write X transpose W matrix, so what will be this? What will be the shape of this matrix? X
Can
is
I?
D cross N matrix. W is D cross 1 vector. What will be the shape of
N
this?
cross 1.
Sorry?
N cross 1?
N cross 1 matrix, right? So it's a column vector, and each entry will be what? So X you can think X transpose will be here. This will be your first example, right? In X transpose, this will be your second example. So this is your X transpose. This is your nth example. And if you multiply it with the W vector, this will be W1 up to WD, right? So what will be the entries in this X transpose W? What will be entry here? It will be X1 transpose W1, right? So what is this? This is the predictions for the first example, y1 hat, right?
Yes, sir.
So in this matrix, this is predictions for all n examples. So this summation I can write as in the vector form x transpose w minus by norm over this, because we are doing square and then summing over this. So this entire thing can be written as this norm over x transpose w minus y, right? In a square over those. And this norm can be written as dot product of these two products. So our task is to minimize this thing. I just wrote this particular equations in the vector form. Right? Okay, so that's the question that you have asked. That, does every model need to pass through the origin? It need not to be case. Let's say
Sir,
assume you have
can you go back a little bit? Just one slide back. Yeah. Here we are minimizing the square error.
Yes, sum of a squared error.
sum of square error W transport X. And that with the matrix multiplication we saw, that is ultimately it is converging to X transport W,
Yeah,
right?
X
And
transpose
this is
W.
nothing but the prediction. Yes.
Prediction for
So
all n example.
yeah, so here we are minimizing the error vectors or sum of error, and we are correlating with the prediction. How it is happening, just not clear.
No, this is not a vector now. This is an I'm taking norm of X transpose W minus Y. X transpose W will be a vector where each entry will be a
Okay,
prediction,
okay.
right?
Not, okay, okay. Now it is
This
clear.
will be
Now
phi
the
one head,
prediction minus
phi n
the
head.
actual, the difference is error, and that is the sum of the error. Okay, okay. Then it's clear.
Yeah, to
Yeah,
take
yeah,
the norm
clear,
of
clear, clear.
difference of that will be a
Yeah,
total
yeah,
error.
sure.
Total sum of total
Yeah, yeah,
error.
sure, sure.
I mean the total
Yeah.
error, right? Okay. So every model need not to
Sir,
pass through origin.
sir, actually, I have the question. Like in the week 5, the
Hmm?
professor is trying to explain in that error the constraint and unconstrained optimization. Like that, I am not aware of this. Shall you
So,
touch this topic
so,
also in this
so
library?
any constraint is associated with it or not? No constraint is associated with it, right? It's just
Sir,
the object.
actually, I have no clarity. Like I forget about the sir, like constraint. Shall you little bit elaborate about this thing? Like how we are seeing.
Constraint means your task, your objective is to minimize this, right?
Yes, sir.
But what if I say I have to minimize this thing, given that I have to choose W from only, let's say, only from some constraint is given, like W1 plus W2 plus
Okay, so we
W3
have
is
the
equal
limit.
to 1. So I've given some constraint to W's, right?
Yes, sir.
So that is called constraint optimization problem. Here, no constraint over W. We can even look for any W in the D-dimensional space,
Okay,
right?
okay, sir.
So this
Thank you,
is
sir.
no constraint is associated with this optimization problem, right? So we will talking about that. Here we are assuming that every model pass through the origin. So any line in the two-dimensional or any hyperplane should pass through the origin. But this need not to be the case every time. And for that, what we will do, we actually allow our model to pass through any. We allow model to be any line, not just the line which passes through the origin. It can be any line or hyperplane that in the space. Okay, so how we can do that? We just add the bias term into that by intercept, right? So if we look at if this will be by equal to mx, if I add by equal to mx plus c, it actually keep track of each and every line into two-dimensional space. So in this manner, if I add the bias term or say intercept term, this is actually called intercept term or bias term. And if I add those terms, then I'm actually looking for all the linear equation, linear lines, right? In the D-dimensional space. So that's how I deal with the problem with the that or the model need not to pass through the origin. Okay, so in this case, what will happen? I'm adding W0 plus W1 X1. That's the same thing up to W0. This is N. This is D. Okay, so I can set X0 as the 1. X0 is equal to 1. So what I can do in the X matrix where it is D cross N matrix. Now I can make it D plus 1 into N matrix where I can add one more feature that I'm calling as a dummy feature. Okay, so what will be the value for dummy feature?
1.
1. So all ones I will add. Okay, so here it will be here, right, in S matrix. So this is your first feature now. This is your second feature. You have D plus 1 feature. So now your X will look like D plus 1 cross N matrix. And what will be the shape of W vector? Yeah, W now will be W0, W1 plus up to WD. So this W gonna be D cross 1, D plus 1 cross 1 vector, right?
I didn't get how it solves the origin. Still not.
Because now since we have allowed the constant term as well, it means we are looking for all the lines in the space or all the hyperplane in the space.
Okay.
Earlier we are allowing only those hyperplanes which are passing through origin.
Okay.
Okay.
This we are doing like in order to fit the data, or like there exists some data for which it passes through. It need not pass through 0.
Yeah, yeah. For let's say for two one-dimensional feature x1 or x1 and y, let's say your data is something like that, something like that. Okay. Now, if I pass, I look for only those lines which pass through origin. It may end up giving me only such lines, right? And I have to look best
Yes.
of this, and error will be high in this case. But if I allow that lines to pass through any point or have a y-intercept, then in that case it will give me those lines as well, right?
Yes, sir. Yes.
So that's how I choose. I I remove the restriction that it should pass the origin. That's by adding the constant term into our space into the equation.
Okay, sir. It's clear, sir.
Okay. Now our problem becomes same thing. We have to solve this problem now. And if you look at this problem, this is a optimization problem with no constraint, and it's a again it's a convex function as well. It's a quadratic function. It's a convex function, and how to solve this quadratic convex function? How to solve this optimization problem?
Actually, shall you go in previous slide again, like that the hyperplane one for hyperplane? Oh, sir. Sir, shall you give the example like that? If you have the 4 to 5 like that feature, so how you like you have the 4 to 5 features. So how you just show in the at a single line, like using a linear
No,
regression,
no,
sir.
that will be a hyperplane.
Okay,
If you have two features, then it's gonna be plane. If you have in a higher dimension, it's gonna be hyperplane, not a line.
okay.
This is the equation of
So like
hyperplane, right? Not
we
just a
get a
line. So W1 x.
we get a one plate at 3D, one plane at 3D, something like this.
So what is this equation? What is this equation?
This equation, sir.
This is a hyperplane, right?
Okay, sir.
And that's what we are learning.
Okay, so we are now learning about a hyperplane.
Yeah.
Okay, sir.
So how to solve this problem? You must have seen this problem, right? How to solve this optimization problem? It's just minimizing a function, minimizing f of x.
Here there
How to
shouldn't
minimize
be
f of x for x?
hello.
Yes.
Here there shouldn't be a summation symbol, right?
Oh yeah, yeah, of course, right, correct. This shouldn't be a summation symbol here. Good point.
Because x is a vector.
Yeah, x is a vector here and take care of everything. It's actually not, this is same as summation over w transpose xi minus by I whole square and I equal to 1 to n. This is what this is, right?
Yes.
Okay, so how to solve this optimization problem?
We need to
By
differentiate.
taking the derivation and equating it to 0.
Yeah, so that's what we do now. We'll take the derivative of this function. This can be written as this dot product x transpose x. I mean, this is your x transpose w minus y transpose this. Take the derivative. It's gonna be 2x transpose w minus 2xy. And to solve for w, I will equate to 0. And when I equate to 0, my w gonna be this thing. So here, this is the pseudo inverse. So this is x transpose pseudo inverse xy. So this is the solution that we are looking for.
Sir, shall you elaborate transfer? Actually, the professor also telling about that. So, sir, what is the? I mean, what the actual difference between the pseudo and that real one, sir?
No,
Inverse.
actually, XX transpose need not to be invertible every time. In the most of the time you will find it's a non-invertible matrix or it's a singular matrix. So in that case, inverse cannot be found. But there's a method of pseudo inverse which is actually it says that it has some property. A matrix is called pseudo matrix when right inverse exists or some properties it should hold. And whenever this is invertible matrix, pseudo inverse actually same as the inverse. That's why we use the pseudo inverse rather than inverse in this case.
Oh, okay, sir.
Okay. And pseudo inverse is actually right invertible matrix.
Right
I mean,
invertible
invertible
matrix.
from the right. Right invertible means invertible from the right side.
Okay, okay.
It means that if A is right invertible, A transpose has to be identity. Okay.
Yes, sir.
So yeah. So this is the solution that we are looking for. Once we have the solution, we are done because we have the function with us. We have found w, and so we have a function y equal to w transpose x. It's gonna be a prediction for any data point. We have w's x, and we can make prediction for every data point. Done. That's
I
what
have
regression is.
sir, I have a request. Maybe toward the end of the class or after the class for 10 minutes, if you could just, like, I tried to solve this by actually differentiating the matrix with a vector, not in a short form, but actual full form.
Which metric?
This one, the LW function.
This one, okay, you are saying the how to
I'm
differentiate
saying
this
one
function.
is to do it in the short form. You can differentiate because xt whatever. But when I do it in the long, like basically differentiating a matrix by a vector, can you just show how to kind of take those and stack up? Because for X transpose, if I differentiate, suppose I differentiate X transpose W with W, I am getting X, but the answer should be X transpose, right? So I'm getting a little confused as to how it's done. If you can just spare 10 minutes and show how it's done, just a little bit of hints, right? Like the gradient, do you stack it column wise or do you put it row wise only? I'm a little confused.
Okay, we'll do that. We'll do that.
Okay.
Actually, I have the proof of that as well written with me.
I've got the proof. I've solved it, but there are one or two places where I'm confused if that's the right way to differentiate a matrix with a vector.
Okay.
With respect to a vector.
Okay, we'll do that.
Yeah, thanks.
Okay. But for now, just assume that this is the derivative for this, and we set it to 0, and this will be my weight vector. Okay, so that's the one way we can solve this optimization problem. There are different ways as well, and in practice we don't go by using this method, because this actually X transpose becomes very big matrix. Dimension of this matrix is going to be very high. Like it is going to be n cross n matrix, right? Sorry, d cross d matrix. And taking inverse of d cross d matrix is going to be very computationally lengthy process, and it takes lots of time in practice. That's why we don't go for using this method. Still, in practice, it says that it always gives you the best solution. It means it always converges to the global minima. Still, we don't go using this method just because of this computational considerations. Okay, and there are different ways to solve this optimization problem as well. That methods are called gradient methods that we are going to learn in. Okay, so before gradient method, there is
Can I
one
please
more thing, which is
interrupt?
geometrical interpretation for this.
Can I please interrupt?
Yes.
Could you go back? Sir was saying that finding the inverse of this matrix was a problem of order D3. So I understand that XX transpose is basically D by D. Where does the third D come from?
Okay, so order of D3, I think
It's big O of
Can I answer that?
okay, as far as I know, I'm not sure still, but as far as I know, this problem has order n d square or d square n d square.
No, D cube.
Yeah, d cube, but
see, can I answer that question? Can I try and answer that?
Yeah.
Whoever asked that, what is the complexity of matrix multiplication?
I don't understand your question.
You're asking D cube operations, right? Computing. That's the complexity is D cube, right? That's the question, right?
Yeah. So how do we arrive at D cube? The D squared I can understand from the XX transpose.
No. That's not how it is done. Have you done PDSA?
No.
Yeah, it will come.
Then you will know when you understand how algorithms compute. See, the simplest of them, matrix multiplication, is also a D cube operation, because you have to multiply row by row and add them up. That is another operation.
Okay.
Right? Even X into X transpose is a D cube operation.
Okay, XX transpose itself is a D cube.
Yeah, because you have to multiply element by element, right?
Then
See, if there's a matrix M into N and N into P, the complexity is M and P, right? You take their constant as D and you say D cube, right? For convenience. So X into X transpose itself is a D cube operation.
Okay, thank you.
Right? Because you have to multiply and then add them up also. That is another extra operation.
Okay, I think I'll reflect on this. Thank you.
Yeah, you can just check complexity of matrix multiplication, but that for that you have to understand algorithmic complexity and all that.
Yeah, thank you.
But if you haven't done those things, you can ignore that part. You just remember this matrix multiplication is of order d cube. The
Right.
computation part is order d cube. It's not the I mean that's this is some different things. You not to worry about those things here. Just remember this matrix multiplication is order d cube.
Right.
It's very lengthy process when d becomes very large. Okay, that's why we don't opt for this method. We go for different method for optimization, optimizing this problem. Okay, and before going to those methods, there's one more thing that we have covered is the geometrical interpretations
Sir,
here.
I have one small question. Can I ask? Small clarification question. Can you go back to the previous slide actually? The formula for W star in the MLF course, I think there is a different notation there. There it mentioned as X transpose X whole inverse X transpose Y. I'm
Probably
just
I
trying to
didn't go to the
understand.
MLF, but probably their X will be of shape n cross D. Here we are sticking with the notation of X to be D cross N.
Okay.
Okay, that's why that's the difference.
Okay, sir.
So in this, we try to figure out what that solution is.
You're absolutely
Okay.
right, because I was referring to the whole nets, sir, and there they've taken, here we have started by X as D cross N, there it is N cross D. That's why it's all opposite.
Yeah. Well.
Sir, can I request, I requested this to Karthik also earlier, across these courses if we can use one common notation, because it's very confusing.
No, but for this particular course, we have used X of D cross N matrix.
Yeah, I understand for this, but for future, I'm generally making a request because I go and refer to all my old notes, and there it's like it's now it's
N
very,
cross D.
it's like,
And in any standard book, you will find it to be N cross D. But
yeah.
we are following this just because professor has also used D cross N matrix, and that's why we didn't use N cross D matrix.
Sir, the same professor used N cross D last time. That's why I got very confused. Anyway, it's not a problem. I'm just saying it.
Yeah. Okay. But you should be compatible by both ways.
So,
It's nothing. It's just one. The notation changes slightly. That's it.
sir, could you please confirm the dimensions of X and X transpose matrices?
X is D cross N matrix.
Okay, and X transpose will be N cross D.
N cross D. Yeah.
Okay, thank you, sir.
Right. So here I'm taking one easy example to understand the geometrical interpretation. I'm taking that Sir has taken. We are taking X of say 2 cross N, 2 cross 3. I mean 3 examples are there and 2 coming from the 2 features. Let's call those features F1 and F2. And so this is how your X transpose will look like. So here it will be first example. Here will be second example. Here will be third example. Right. This is how your X transpose will look like. Right. So F1 and F2 are the 2 features. I'm calling. So for this, let's assume your features are height and weight. And for first example, height is let's say 170 and weight is 70, and here 168 or 75 or 162 or 60, something like that. Some 3 examples are given. This is first example. This is second example. This is third example. So this is your first feature. First column vectors of X transpose are column vector, right? Column vector of this will be the feature space. So this is your first feature F1. So F1 are coming from R3 here, and F2 again is coming from R3. In general, F1 or FD are coming from Rn, right? So columns of Xn. So I'm looking in the space spanned by the columns of X transpose. Okay, so let's call those F1. So it need not to be orthogonal every time. So I'm calling this as a F1. This is the first column of X transpose. This is the second column of F transpose. Or this will be my space spanned by the F1 and F2. And this is somewhere here. This is my Y vector. Y vector is again coming from R3, right? So now I will interpret by in terms of F1 and F2. I will try what the solution actually looks like. Okay, so if I take the projection of Y3 onto the space spanned by F1 F2, so this will look something like this. Okay, this is the projection of y by head. Okay, so and since I'm taking the projection of y hat in the space of f1 and f2, spanned by f1 and f2, I can write by hat as the linear combination of f1 and f2, right? And what I can write is as x transpose alpha, right? It's a linear combination of f1 and f2. Can I write something like this? It's a linear combination of those spans, the basis, right? Not just basis. I mean, I'm looking for the space spanned by f1 and f2. So I can write a y hat as a linear combination of as a f1 and f2. Not y hat. It's a let's call this by let's call some different thing. What projections I'm calling it. So let's call it by one.
So, sir, what is the main function of y? It means y is something different from feature, no?
Y is the level vector.
Okay, so y is the
for in this example, y will be a three-dimensional vector, right? So it will be some, let's say we are predicting something else using height and weight. So some quantity we are assuming, calculating. So let's say BMI we are predicting. Okay, so here it is some 20, 18 or 25. So this is your level vector by here.
Yes, sir.
Sir, I think I was quoting this example only. You remember at the beginning of the class?
So then, what is the F1, F2 here, sir? This is the element of X matrix.
Column of X transpose or say rows of X.
It's okay.
Sir, now can I ask my question? I think I was asking this only at the beginning of the class. Then you said, we'll discuss.
Yeah.
So I was saying that, till now, whatever our understanding is that, all the features put together, they form one vector. Say, for example, as you have taken here height and weight, right? So if I take a vector height and weight, so 170 and 70, this will form my one vector. Means one data point is one vector, right? But
so
here
this is your X. Yeah,
here what professor is saying that you put all the height in, all together, all the height together, and then call it as one vector. So this point is not clear to me, because whenever we are saying a vector, it means all the elements are different features. But here all the
so that is a data point. So if you look at 170, say this vector 170, 70.
That's a
data point.
And
X1,
that's a vector. That's a vector
but
format.
if I look at only the first feature values for all examples, here we have 3 examples, and I just look for the first feature value 170, 168, 162. That is your first feature f1. Okay, so what we are looking here, we are looking only for the features values, first feature values.
But why we are doing like this? How it is helping us?
Yeah. So this is called feature space. So this is one feature one values. This is your feature two values for the training example.
Because starting from unsupervised learning to till now, our understanding is that whenever we are saying even feature space, so different elements belong to different feature. Say for example, in the case of earlier examples where we were dealing with 4 or 5 features, right? Or even 100 features. So one vector, it means it has 100 different elements, right? Coming from different.
So that we are referring to a data point, particular data point.
Yes, that's a particular data point.
Yeah, so here what we are doing in that space, we are making the features. This f1, this is your feature space, and here is one vector f1. This is the second vector f2, and that's it.
Okay, so just correct me. So it means that whenever we are talking about feature space, so it means all the elements of that vector belong to the same feature.
Yeah, same feature f1.
Okay.
Sir, hello, sir.
Yeah.
Sir, can you please give one very small example that from among all the data points, how can we find out W?
That will be a computationally lengthy part, because that you have to solve X transpose this equation, X transpose inverse XY. You have a X with you, you have Y with you, then you can use this equation. You just solve this equation and you will get the W vector. Right? In this case, this is your X transpose. This will be your X in this case. 170, 168, 162, 70, 75, 60. This will be your X. You have Y with you. You have Y as 20, 18, 25. So solve this equation, you will get your W star. Okay. So coming back to this point, I am just taking the projection of the bi hat into the span. So bi one here is the this is the projection of bi hat. This is not bi hat. This is actually a bi. This is your actual label. So I should call it
Correct.
bi
This is
one.
why. Yes, yes, I was coming to it.
This is bi, or let me call it bi one. So bi one is the projection of bi onto the span of F1 and F2. Okay, so can I write by one as a linear combination of F1, F2 because by one actually projection into this space. So by one lies into this space. So I can write it into linear combination of F1, F2. So I can write it as F transpose alpha for some alpha. Alpha is coming, again coming from RD. In this case from R2, sorry, Rn. Right. So and so what will be this thing, this particular vector?
Error, right?
Error. Yeah. What will be this? This will by minus by 1, right?
Yeah.
This particular vector, if I draw this vector, this gonna be by minus by 1. Okay. So if I take this product, because this is a projection, so this product of this thing gonna be 0. It means, or say this gonna be 0. I'm writing it here. So this product by 1 transpose by minus by 1, it is, or say it is gonna be 0, or say by minus by 1 transpose by gonna be 0, right? Sorry, by minus by 1, this is gonna be 0, right? Because these are orthogonal, this is, and this is are the orthogonal. Okay, and if I I replace by 1 by this x transpose alpha, by minus by 1 transpose x alpha equal to 0, and this should satisfy. And if I take alpha as a W star, whatever I got here, alpha is W star as XX transpose inverse X by, if I substitute there, you see that this satisfies this equation. It means that alpha equal to W star is the solution for this alpha, right? Or what we can say that this by 1 equal to X transpose W star, right? So what was y1 your? Y1 was the projection of actual label vector. And what is X transpose W star? What is X transpose W star? What is your X transpose W star?
Projection, isn't it?
X transpose a projection that we have come here. That X transpose W star is the projection.
Is it Y1?
But what was this? Wasn't this projection for every Y?
Yes.
Yeah.
Right. So what we can conclude from here? This prediction is projection of the actual label vector by onto
Features.
the space spanned by F1 and F2. Space spanned by F1 and F2. Right? So this is the statement that, right? So predictions is the projection. What if I call that by lies into space of F1 and F2? What will be the projection in this case?
It is 0.
If the label vector itself lie into the span of this, what will the projection?
0. Sorry, projection will not be 0. Projection will be the length, actual length.
Projection will be by itself, right?
Yeah, by itself.
So what we are predicting actually in this case, the actual labels we are predicting. And what will be the error in that case then?
0.
0, right? So whenever I say that the actual labels are lying into the span of features F1, F2, then the error will be 0. If that is that estimate true or false?
True.
That is true, right? So keep in mind this thing. The prediction that the linear regression model gives is actually the projection of the label vector onto the space spanned by F1 and F2.
In general, we won't have that situation, right? It will be always out of the feature space, right? Is it not? Y lies.
Yeah, in most of the cases, by should be out of the span, the space spanned by F1 F2. But if it lies in the space of F1 and F2, then the error will be 0. It means that we are predicting the actual level for every data point,
Yeah.
right?
So does this mean we are overfitting?
No. In that particular case, we are not overfitting because the data, the distribution is kind of very. There is no error in the distributions. I mean, or you can think as they are coming from a line itself. All the data points are lying on a line or on a plane in the
It's like,
or
yeah,
on a
it's
hyperplane in the
correct.
right.
It's like, yeah, it's like on a line or a plane. So the prediction
Yeah,
will be deterministic.
yeah. So error is 0 in that case, right?
I have a question. We're taking 2 features and we're computing this. If the third feature comes, does it mean I'll have to do 3 projections or?
No, the projection is span of. Then we will look at the span of F1, F2, and F3
at the same time. Okay.
Yeah. Okay.
I'm just wondering how the math will work over there. That's the reason. Okay.
So in that case, it's the span not gonna be a plane. It's gonna be some hyperplane. Here it's only F1, F2. Then we can think it's space spanned by F1, F2 as a plane. But in that case, it's not gonna be a single. It's something hyperplane that we cannot geometrically visualize.
Okay.
So okay. So that will be a different thing. But it holds for any D-dimensional D features.
Okay.
Yeah. So we have look for one methods to optimize this problem, but this optimization problem has one problem of the computational consideration it has. So we go for different methods to optimize this, and we have the gradient descent methods to optimize that particular problem. So have you ever come across this gradient descent methods for optimizing any convex function?
Yeah, in MLF.
Yeah. So what is gradient descent? Let's say you have been given a function f of x, right? And you have to find the optimum value. So what gradient descent says, you start with a random point x. Let's say we start with a point x0, and we'll look at the loss at x0, right? So let's assume you have some function f of x, something like this. Okay, this is your x, this is your y, so this is your f of x, this is your some loss function. Okay, so you start at a random point. So you start from x0, and the x0 you look at the loss function
Sir,
value.
sorry, sir, can I ask one question? Sorry, just going back to the last one. Can I just stop you for 1 second?
This one?
Yeah, no, sir. So this pseudo inverse and all is required, one, because you'll have the number of data points will be far more than the number of features usually, right? I mean, generally in this kind of cases.
Generally, this matrix is known is singular matrix. This x transpose matrix is singular matrix.
No, that is if it is square. If it is not square, also, then whatever it's called, right? If it's not,
It's
a
always
square,
a D cross D matrix. This x transpose is always
X
a D cross.
transpose will be a square matrix.
not XX transpose. I'm talking about the original equation, right?
X matrix.
X
X
matrix, right?
Square matrix.
Yeah, so it will never be a square matrix. Even if it is a square matrix, if it is singular, you'll need the pseudo inverse anyway, correct? Right? Because
yeah,
because y will not lie in the column space of x. That's the problem.
No, we are not adding y into the x matrix.
No. I'm saying y will not lie in the column space of x. That's why we won't have a solution.
You have a solution, but projection will be the solution, not the by itself. The projection of by on the space spanned by f1, f2 will be the solution in that case.
Yeah. That is
not the solution. That the predictions will be that.
Correct. Prediction will be that. But yeah, I think we're saying the same thing. Got it.
Okay. So here gradient descent, how it works, we start with some point, we check at the loss function value. So we'll check the function value f of x. Then we try to move in that direction where loss decreases, right? So here, if we started from here, we try to move into this direction. And how to find this direction? This is actually we can find using the gradient function. Gradient for any function f at a point x0 gives the direction of maximum change. Okay, so remember this statement: gradient at any point, let's say at gradient at x, for scalar function f of x gives the direction of maximum change in that function. Okay, so if I look at this point here, at this point, the gradient will be in this direction, because in this direction the function change is maximum. Okay, so where we want to move to this point, right? So we want to move into the negative direction of gradient, right? So what we do, we start with some point x0, and we then look at the loss function value, and then we will try to move into direction of negative gradient. So that's the idea behind gradient descent into the direction of negative gradient. Okay, so this is GD, and this is gradient descent, and why we need this, because the normal equations is not preferable every time. That's why we go for the different methods for that. And so this is how you denote a gradient for a function. This is again a vector quantity, right?
So,
Yeah.
so I have a question. Is the gradient descent algorithm is applying on like that the predicted value, or in the value already we have, like where we are applying this gradient descent?
On the loss function, we have a loss function, right? This loss
Oh,
function,
yes, sir.
norm of x transpose w minus pi whole square. This norm function. This is the loss
Sir,
function.
so my question is, this loss function is a quadratic one?
Yeah, this is the quadratic equation in W.
Oh, okay, sir.
It's a convex function, right?
It's a convex function. So in convex function, all the local minima are low. There is only one global minimum.
Yeah.
Okay. So we want to move in the directions of the function values where the function value decreases, and actually move in the direction of negative gradient. We can say it. Negative gradient. Okay. And how much steps to take, that is handled using some constant term which is called learning rate, and it's actually hyperparameter. So what is a hyperparameter?
Feature matrix, I mean feature value of
So
the
parameters which we can change, parameters like weight here.
So those parameters which actually cannot be learned using the model itself. Remember, those weights are actually learning using the model, but these parameters model cannot learn. So this is the one which our user we have to set by manually set those parameters, and we have to check using different values and check which is going to best one. We'll come to hyperparameter later, but remember the direction that we are moving in. That is how much to move in this direction. It is handled using
What
the
is
learning rate eta.
hyperparameter in case of regression, sir? What is hyperparameter in case of regression?
In this case, it's the learning
Okay,
rate.
eta is the hyperparameter.
So,
right.
Sir,
So
actually, I have the question, sir. Sir, like that, what is the difference between the feature and the parameter, sir? Like that, we have the, let's suppose we have the one vector and we have the three features. Okay, so if I'm saying it's have some kind of parameter, so what is the parameter in that vector?
In this case, parameters are this W is the parameter, and features are dot F1, F2, F3. Parameters
Okay, so
are
W
one which are
itself
learned
is the
using the
parameter.
model. Huh?
W itself is the parameter.
W is the parameter.
Okay, sir.
Priyanshu?
Yes.
In a normal terminology, I think, sir, you can correct me. We use parameter and feature interchangeably.
No. Never.
Sir, parameters everywhere we use parameters. What are different parameters?
But parameter and features are different things. We don't use.
But I am coming in case of regression weight. We are calling weight as parameters. Okay, I take back my statement. When I come across in any book that I will post it, we can proceed. Yeah.
No. See, whatever you are trying to estimate, whether it's statistical, Bayesian, gradient descent, whatever you are trying to estimate, that is called a parameter. Right?
Yeah. So in this case, W is unknown quantity, right?
Yeah.
That is learned
W
using
is what you are trying to estimate. So that is the parameter.
You're trying to learn, right? So these are your weight vectors are actually learned using the model itself. Okay. But these etas cannot be learned using the model itself. These are the user set quantities parameters. So these are called hyperparameters. Okay, so what gradient descent says, we start with some W0, some initial values, weight vector. Then we will move into the direction. So the next weight will be we move into the direction of the gradient descent. So we'll negative gradient. So this will be the gradient at W0. We move into the direction of the negative gradient, right? So let's say that Tth iterations, Wt is the weight vector. In the t plus 1 iteration, this will be the weight, and how we will move? We will move into the negative direction of the gradient, right? And how much to move? This is settled by the eta. And what is the gradient? Gradient is just the 2xx transpose w minus 2x y. Okay, so that's how
Sir,
we can update our weight vectors. And
so sir, shall you show how the WT1 is equal to like that that last one, the last part 2xy, sir?
so
How
this
we
is
got that? Shall you
this
show
is
that,
the
please?
gradient of f of w. So
Okay, okay.
f of w was this loss function, right? X
Yes, sir.
transpose w minus pi
Yes, sir.
transpose x transpose w minus pi. So if you take the derivative f of w, this is gonna be this x transpose w minus 2xy.
Okay.
At the moment, we are under some timeline that we have to meet, especially in light of the deadline for the graded assignment. On a day when you have a little more time, would it be possible that you explain these opening of brackets with transposes? Because I'm not from a mathematical background and I find these difficult to evaluate and arrive at whatever we usually arrive at. So if you
Okay,
just tell
you
me
want
some
the
simple rules for opening the transpose outside the brackets in case of a big function with their plus minus signs and everything. So maybe not today. We can do it on a later date. If
okay. So what we can do in the next session of this, we'll do this part, right? So I think someone has also asked me to do this derivative. So this is how your function looks like.
Yeah.
Take the derivative with respect to vector, so that we can do in the next session. Of
Yeah.
Thank
So
you. Yeah. Thank you.
what she asked is a very right question, because when we have to swap and things like that, when do you move? When is it okay? Because the dimensions of matrices are different. I
So
think
that
that's a
is
very good.
actually basic linear algebra stuff, right?
Yeah.
Okay.
Yes, but we
So
seem not to have done it so far as the
my
transpose comes outside the bracket for such a long function.
no, my confusion is not that, sir. That I am clear about. My confusion is when I take a matrix and differentiate it with
Yeah, I got.
respect to the vector, how to do it. That's a very different question.
Yeah. I know that.
Yeah.
We can also do that in the next section of that. I
Sure.
think.
Sure.
Okay.
What
So when is the
exactly is
deadline for week 5?
4th?
4th.
Friday.
Okay. And what about week 6?
Sunday.
That will be 7th.
No, I think next Wednesday.
No. Sorry.
Next
Are
Wednesday.
you very sure? I thought it was showing Sunday. Just let me check.
No, I think they've changed
Okay,
it.
so if deadline is extended, can we move week 6 session to next week?
Week 6 is 8th of March here.
8th of
8th
March.
of March. Then can we move week 6 session to the next week?
Yes,
Yeah.
definitely.
Yes, sir. Yes, sir. We have a lot of
Sorry.
doubt from previous week also.
Hold
Previous
on.
week also.
8th is
We will
Wednesday.
discuss.
8th
When
is
will we
Wednesday.
move it to? 8th
Yeah.
is Wednesday. Which week will we move it to?
That week only.
I mean,
Monday, I think. Monday maybe.
Monday, Tuesday, whatever that suits.
Monday, Tuesday, and then 8th is Wednesday.
One day
Yeah.
will not be enough for week 6.
Okay, we'll figure out the date for week 6.
No, the coming Thursday session, it's marked as week 6. So we could take that as week 5.
No,
Correct.
And
that's
then
fair enough.
Friday session as week 6 itself.
That's
Yes.
fair enough. Friday
That's
we
a
can
better
cover
idea.
regression, and then Saturday and Monday week 6. Yeah.
Okay, so there is no session on Thursday. I will take one session on Friday that we can take for week 5.
Right.
Then there is one session on Saturday that we can take for week 6. And
Yep.
we can plan one more session on week 6 on the next week. I mean the Monday or Tuesday, whatever suits that day.
Yeah.
Okay. Yeah. So that's how we make the updates. So any doubts in how we make the update in gradient descent?
One question: what exactly is eta here? Sorry, I missed that
Eta
part.
is a constant here. It's a learning rate. How much to move in that direction?
And we fix that, or is there a way of actually?
So this learning parameter, this is a hyperparameter. There's a different ways to set this. But for now, assume this is a constant. Okay, so in the higher courses like deep learning, you will see this how this is affected, how this affect your model, this learning rate. And there's different ways to set this theta, but for now, just assume it's a constant.
Okay.
Okay. Okay. So one more thing here in the gradient descent, like just always remember this picture in your mind. You have one loss function surface, some parameter here. This is the loss function f of w, or let's say loss function L of w. Let's call it. We start from some point. We want to move into this direction. We always take move into this direction, up to this direction, and how much to move in every iteration it is set by eta, and it may be a case that in the minima, this is your minima, here we want to reach. It may be the case we can overshoot and reach in this direction. Again, we will find the gradient at this point, and gradient says that move into this direction, and then we again go back. It may be case that it again keep on oscillating into this direction, but after some iterations, and this gradient value and this step size, make sure that it always move into direction of the negative, I mean the minimum, global minimum, right? Okay, so that's why because of step, if we choose larger value of this, it may be the case that let's say you have this loss function and you have chosen large value of eta, then it may be it may case that you want to go here. If you've chosen large value of eta, then you can move to here, and then again you have moved to here, then here. So, and you are not reaching to global minima. So in that case, what you will do, you will try to decrease the value of eta, right? And very less value of eta may be cause of very slow convergence, like it is moving in the right direction but very slowly moving into that direction. If you feel that loss function is decreasing but decreasing very very slow, in that case you can try some larger value of eta, right? And if you feel that eta values are oscillating, I mean the loss function is increasing then decreasing, or increasing decreasing, something like that, then probably you should set lesser values for eta. Okay, so step size decides how fast you are moving into the direction of local minima, whether you are oscillating or something like that. So it's all observations that you have to make when you solve such problems, and then you have to set these eta values. And there are different values to different ways to set eta. It may be a function of iterations, it may be a constant, depending upon situation, given problem and at hand. Okay, so, but for now assume eta is a constant term. It probably you just set to some lesser values, generally set to lesser values, because we don't want to overshoot every time. Okay, so that's how
Sir, what is hyperparameter?
Hyperparameters are those parameters which are actually not learned using a model. The user has to set those parameters. Users has to come with the best values for that. Model itself cannot learn those values.
So in
Like
this
eta.
case, eta, yeah, okay.
Yeah, eta itself cannot be learned using a model. Model only learns those weight vectors using the training example. But eta, you have to figure it out what best value suits for your model.
Okay.
Sir, figuring out this like the
Figuring out
hyperparameter
will you
requires
set some
some
eta.
domain knowledge now.
Domain knowledge, and whenever you start modeling, you will fix some value of eta, and we'll check how the loss function changing per iterations. Then you probably go for some different values of eta, and there is some cross validate base to tune your hyperparameter. But for now, you just assume it, in this case it's a hyperparameter which is a constant term. Okay, so how to find the hyperparameter, that's the different thing that we'll learn in some different courses, not in this course.
Okay, thank you, sir.
Okay.
So, sir, linear regression inherently use the gradient descent to reach the optimum
Global
value.
optimal value, yeah, minimum value.
Okay.
Okay. Again, if you look at here, it again uses derivative of f, and it's again x twice of xx transpose. What is the gradient xx transpose w minus 2xy? Again, the problem of the computational. Here, xx transpose again comes, and again this is d cross n matrix. So this this matrix multiplication again is very very lengthy task. So avoid this thing. What we do, rather there is a different version of gradient descent. One of those is stochastic gradient descent. What we do, rather what we have done in the gradient descent, we have at a point x0, we find the gradient direction, and the gradient, for finding the gradient direction, we make use of all the data points, right? And which gives me the actual gradient direction. So rather than finding gradient for all n data points, we only make use of lesser data points. So what we do here, we make the different batch of the data points. Rather than having n, let's assume we have 100 data points, or say 1000 data points. We divide those data points into different batches. Let's say we have divided into 10 batches, and every batch has 100 data points. Okay, so what we do in stochastic gradient descent, rather than finding the gradient for 100 data points, we find the gradient only using these 100 data points, and then we'll move into this direction again. Then we update our batch, and for that updated batch, then we will use the next batch. Okay, and once we have used all those 100,000 bits, then we will call that one epoch.
And
Okay.
how to actually group this 100 out of the
It's
1000?
randomly chosen. They are randomly chosen.
Okay.
Sampling,
yeah. Okay. So one question here. Since we are using only, we are not using all the data points. We are using only some subset of those data points. Will the gradient be the right direction to move?
may or may not be.
Yes, of course. It's not the actual direction that we want to move, but on aggregate, or all on the in the last, we actually moving into the right directions. Okay, that is confirmed using stochastic gradient descent, and the last bit that has taken as all the weights, we take the average of all the weights. Okay, T is the iterations. Okay, so every iteration, it may be the case that we are not moving to the right directions, but that is a greedy approach that we accept. Okay, and in the last, there may be lots of iterations to convert, but in the last, we will tend to move into the right direction. Okay. Yeah.
So the T rounds is like bootstrapping, right? We do it T times.
T is the number of iterations. Yeah.
Yeah, it's not an iteration in one. See, when let's say we're not doing stochastic gradient, we're just doing normal gradient. Then every time it goes forward, right? It approaches toward the global minimum. That is also called iteration.
Yeah,
iteration. We are not calling that as this T, right?
One update of a weight vector is called one iteration.
Yeah. So let's say in stochastic gradient, let's say I do that once. Then I do it all over again from the beginning. Then I do it all over from the beginning. This is what you're calling as iterations, right? Here in this case.
Yes.
Yeah. Because in each gradient, in each stochastic gradient round, also there will be some iterations. There could be whatever.
Yeah.
K iterations.
Yeah. And if you have 10 batches, you have 10 batches. Once you complete all those data points, then that is called one epoch.
Okay.
Okay.
The last
Sorry, what is the word you're using?
Epoch.
Epoch.
One epoch. EPOCH.
Sir, what is epoch, sir?
So let's say you have 1000 data points and you make 10 batches. So in every batch you have 100 data points, and you just make sure that they are not overlapping.
Yes, sir.
With disjoint sets. Once you go through all those 1000 data points using those 10 batches, then those complete cycle is called one epoch.
Okay, so we will run 2 to 3 times like that, no?
10 times we have to run. In this one epoch, the 10 iteration weight vector will be updated 10 times.
Okay, right? Sir, so if you are telling that it's running at 10 times, it means for each data set, or you are for 1000 or for 100?
For 100 we are making, for 100 we are taking the gradient, we are calculating 400 data points in one round, one iteration.
Yes, sir.
I can understand this actually.
Sir.
Epoch is what is one batch of 100 data points?
Yeah, correct. So
One
let's say,
epoch means we are covering the one batch.
can I try and answer that, sir? Tell me if I'm correct, right? I'll also be clear if my understanding is correct. Let's say there are 1,000 data points. You break that up into 10 epochs, right? So 100,
10,
100,
10
100.
not 10 epochs, 10 batches.
10 batches, okay. So each, you take the 10 batches of 100 each, right? So you take the 100 and run this gradient descent. It may do some iterations and it will come to some final weights, right? Then similarly, you do it for the next batch, then the next batch, then the next batch, 10 batches, and you take the average of the final weights.
Final weights.
Okay, got it.
So one more clarification here that you have 1,000 data points, right? And now you have made 10 batches. So let's say 10 batches will be of 100 example. In this batch will be 100 example, and up to 10 batches you have 100 example, right? And assume all those to be disjoint one, right? So what you will do, for updating the weight vectors, first you will make use of those 100 points and you will update your weight vectors. Let's say initially you have W0 weight vector. Now you have updated your weight vector using those 100 examples. Again, you update your weight vector using 100 examples that you call as W2. And you have updated weight vector up to for using 10 batches, and you have updated your weight vectors from W0 to W10. Okay, so these 10 updates itself, all those cycle is called one epoch. So one epoch here in this particular case will be 10 iterations, or say 10 update of weights.
One fundamental question. What exactly does weight represent here?
Weight is that we are moving, right? Weight, that what we are trying to find out.
W.
Weight.
So in a simple term, can we say coefficient, sir? Like we use a coefficient in X.
Coefficient?
Yeah. Correct. You're right.
Sir, what
you're right,
you
GP.
achieved...
Coefficient, parameter, weight is the same thing here.
Can you go back to the previous slide, please, where you had written that delta F of... Okay, with the features, I'm actually W of t
So
plus
here
1,
in gradient
W
descent, what's happening? We are calculating delta F as this 2xx transpose, right? So in the gradient descent, we are using this as n, this xx transpose as n cross n metric. But in the stochastic gradient descent, we are not making use of all n examples. We are making use of some subset of n examples. In that case, it's gonna be n1 cross n1 metric, right?
Right.
So it has decreased the size of this metric xx transpose. Okay,
Sir, after completion of this one epoch, we would repeat the cycle, right?
Yeah, we'll repeat cycle, and in this repeating of cycle, we again make the batches. So it's not like we again make those batches randomly, right?
Okay, so those batches would be different from the initial epoch batches, right?
Initial epoch, yeah.
Okay, and this we will continue until we reach the minimum.
Minimum value, yes.
Okay,
So
thank
you're
you.
saying weights is...
we have
Go on, Divya.
in one iteration we have done on each of these 10 batches. Just update
one by
from
one, all those
WT to WT plus 1. From for updation of WT to WT plus 1, we have done it for each of these 10 batches, right?
One for one batch, we find the gradient and update our weight.
That would be WT plus 1.
WT plus 1. So
and for the second batch, would you do the same thing?
Same thing. In that case, it's gonna be WT plus 2.
2. Okay, we're doing it T plus 2. That means
yes, this superscript actually denoting the iteration number. This is your iteration number.
So we're updating.
Sorry, we are in one epoch. We are updating your weights 10 times.
Divya, you're not audible.
Sir, can I ask you?
Yes.
But WT plus 1 is not the final. It's the final weight, right?
WT is the weight at the T plus 1 iteration.
So every time you're running that epochs, I thought for one epoch we run the entire thing, then another epoch we run the entire thing. So can we can I just ask? Can you go to a plain paper, sir? I'll lay it
Okay,
out out
let
not
me
very
do it again and let me know your doubts. Okay, let me do it again. Okay, so what we do in gradient descent, we update our weight vector as this, as follows: W t plus 1. Let's say at t iteration you have weight vector WT. Okay, this is your weight vector, right?
Oh.
And now you are updating as you are moving into direction of gradient, negative gradient, eta times del of f, right?
Oh.
And you compute del of f at the point that you are currently at.
Oh.
Right, and you can write it as WT. This is T is the iteration number, okay? Eta and gradient will be your 2 times x transpose y minus xy, right? Okay, so this x is actually your taking all n examples.
Yeah, here we're taking whatever n by k being
N
the batch
examples,
size.
right? For all n, and we are making update. But what happens in stochastic gradient descent, we don't use of all n examples. What we do, we divide all those n examples into different batches. So let's call those n1 up to n10. We have make 10 batches, and all 10 batches contain n1 examples, n2 examples, and n10 examples. Okay, equal examples. Okay. Now for updating a weight, let's assume at t iteration you have weight vector t. For t plus 1 iteration, let's call t. At t plus iteration, what you will do, your theory says it move into direction of gradient, right? For calculating gradient, this will be minus eta 2 x transpose by minus xy, right? So here you are not making use of all n examples. You are taking this batch example. So here computing gradient, you will make use of all n1 examples, right? So once you use all those examples, this is your next iteration. Again, you will do t plus 2 second iteration. You will make use of t plus 1 weight, whatever you obtain in t plus 1 iteration.
Correct.
In this example, when you calculate the gradient, you will make use of all those n2 examples.
Correct.
And again, you will do t plus 3. You will make use of t plus 2 weight, the weight obtained in t plus 2 iteration. Here, you will make use of all n3 examples to calculate the gradient.
Okay.
And you will do for all 10 batches, right? Once you have done with all 10 batches, those 10 update, you have updated weight vector 10 times, right?
Okay.
You have updated you have gone W2 to WT plus 1, and again you have updated weight here. You have updated weight here. You have updated your 10 times, right? In 10 time updated, you have make use of all n examples, right? Those 10 updates are called one epoch.
Correct.
And you again start doing this. Again, you will make some batches, 10 batches. Then again, you do 10 updates. Then it calls next epoch. Then again, you keep on doing till you converge to the minima.
No, when you're doing the next epoch, are you starting from WT plus 10 or are you starting from WT?
No, you are starting from WT plus 1. WT plus 10.
Acha, you're starting from WT plus 10.
Yeah.
And that
So the
batch
weights are
of
updated.
that batch of N1, would it be the same N1 that you did in the
No,
WT plus
you
1?
can shuffle them. You can change them. Okay.
The weights are updated between when you're in between the epoch when you're going. The weights are updated or the weights are kept the same. What exactly are we actually trying to do?
Weights have been updated.
So we are progressing from 100. I start with WT. Let's say the next batch I'm WT plus 1 on the next batch. So I actually am at the end of it T plus 10.
Yeah, you are WT T10 T plus 10.
So in middle of the epoch, if the convergence happen, what happens? We stop there.
You stop there. But generally it doesn't happen. Your surface, you may start very far from your local minima, and in general
at some point it will converge, right? So it could be
converge. Yeah, it may
what I thought was, so when we are moving from WT to WT plus 1, right? I run the updates. I run the update on all the 10 batches, okay, and I take the average of those 10 for WT plus 1.
That also can be done, but the theory says that you update every time for every batch.
Yeah, because what I thought is from WT to WT plus 1, I run it once, Okay, I run all the 10 batches. I get some WT1 at the end of it, right? Now then I run 4 such epochs, let's say. So I get 4 WT plus ones. I take the average of that, and then I'm at WT plus 1. Then I repeat the process all over again.
No, I got your process. Just one question for you now. As you are saying, you are going from WT to WT plus 1 for all 10 batches, right?
Correct.
But then how you are making updates?
No, I'm not making an update. For each run, I'm seeing what is the WT plus 1. Okay. And I'm taking, like, I have 10 WT plus 1s. Let's assume there is only one epoch for now, just for the sake of discussion.
Okay.
Right. So for at the end of those 10 runs, I get 10 WT plus 1.
Okay.
Now I take the average and my weight is updated to the average WT plus 1.
Okay.
Now I repeat the process, and from there I move to WT plus 2.
Yeah, that is also can be done. That is not an issue. But most of the standard book you will find that you don't take average. You just keep on doing this process again and again until convergence.
I think the professor has also said to take the average, because there is a formula 1 by t summation of I equal to 1 to t and WT, and where he is saying
that can also be done.
That's where he is saying that guaranteed to converge to optima with high probability.
Yeah, that also. But if you look at any standard book, stochastic actually makes only one make weight of every example. So here you make 100,000 examples, then you update for taking each and every example. It means that you take the best.
Just explain the process yours again, sir. So I am starting at WT. I have one batch of 10. I run it and I update it to WT plus 1.
Yes.
Then I run another one. I move to WT plus 2. Then I run, and at the end of it, I'm at WT plus 10.
Yes.
Now so one epoch is done.
Yeah.
Now I move on to the second epoch, and from WT plus 10, I move to WT plus 11.
Yes, WT plus 11. Yeah.
Then WT plus 12.
Yeah.
Until the time it converges. So it may stop in the middle epochs.
Yes,
I actually understood it the other way around. I thought each step you do all the simulations and take the average rather than progressing continuously.
No, in most of the cases you continuously progress and don't take average of weights. Okay, so ideas of that sir has mentioned about taking average, maybe something like that. So what we do in the stochastic gradient descent, we don't move into the actual gradient direction. Let's say we have something here, and since we are not making use of all the example, negative gradient may be in this direction. It's not this direction. Okay, and again you do for some reference base size, there will be some this direction. You are moving into this direction and this direction. So taking average, make sure that you are in the last you are moving into the direction of gradient direction, negative gradient direction. So that may be the idea behind taking average, but in practice it's actually go in the continuation. You don't take average and keep on moving, once you take the step here, you may be in the wrong direction, but again you start from that point and then move into some direction. Okay, so in the last you converge to the global minima.
Hello, one doubt. That W2 updation, it is for only the N2 batch, right? Not for
N2 batch. Yeah, N2 batch.
Sir, the updation rule is WT plus 1 is equal to WT minus eta into nabla WT, right? Yeah, got it.
Nabla.
Sir, one question, sir. We are updating this weight based on this gradient, no, sir. So what is the role of neta over here, sir? Like, will it be any constant, or like?
It's a constant. It actually decide how much step to take into that direction.
Like in each iteration, we need to change that, or like we should keep it select a constant at the beginning, and
you can choose as a constant in the beginning. Generally taken as a very less value, you can start with 0.01 or 0.001. 0.01 is the right choice for a toy data set, but depending upon data set, this value can be lesser, can be higher as well. Okay. Okay, so this is all about gradient descent and stochastic gradient descent. And since we are making use of some subset of data points, this become now n1 cross n1 matrix of shape n1 and n1 cross d cross n1. So this multiplication now somehow get less computationally lengthy, right? So okay, so this is about gradient descent and stochastic gradient descent. And now, so we have seen two methods of optimization. One is called normal method, which actually gives the actual minima, the global minima. But there is problem with the computational lengthy. Then we go for the gradient method, right? And gradient method, we have seen two methods. One is vanilla version is generally called, but you can just call it the gradient descent. Okay, so there's different version of gradient descent. One is of one out of those, one is called stochastic gradient descent. Okay, there is also many ways gradient descent. So whatever we have discussed is actually many ways gradient descent. And if we take base size of one, then it is called stochastic gradient descent. But for code, sir has mentioned stochastic only. So you stick to this. Stochastic gradient descent is taking batches and then make the operation. Okay.
What is
We,
that
we didn't have vanilla.
MBGD?
We have a sir vanilla version.
Vanilla version is the common where we take all the examples to update, make the update.
Okay.
What was MBGD?
This is what many were gradient descent, but we haven't discussed this in the course, so leave it. Actually, whatever we have discussed here is called many ways gradient descent. We make the batches and make the iterations. If we take batch size of one here, I mean in each batch, if we take only one data point, then it is called stochastic gradient descent.
Sorry, if we take
Batch size of one, it means if in every batch if we take only one data point, then it is called stochastic gradient descent.
okay.
Okay. So
Sir, is there a possibility of discussing one question from the quiz, sir, or we can't?
there's lots of part remaining for this. Can we do in the
Okay. I thought it's over. Sorry. Sorry. Kernel regression is there. I'm sorry. Oh, probabilistic view. I'm sorry. I thought it's over. Go ahead, sir. Sorry.
Okay. So till this point, any doubt? Okay. Now let's move to the probabilistic view. So we have designed our model, right? Now we look at another point of view for this model. Okay. So what we are assuming in this probabilistic view is that let's assume your data set is coming from some function y equal to f of x. In this case, let's say y equal to linear equation y of x. But those data points are coming is adding some noise, right? So they are coming through this line, but some noise is added to every data point. So this is your noise, right? And the assumption that we make is that this noise, let's call it epsilon, actually follows Gaussian this normal distribution with mean 0 and some variance sigma square. That is the assumption we make in the linear regression model. And this is valid in assumption as that, because you see Gaussian normal distribution is seen in behavior as well, right? So this error that for every data point there is some error associated with it, right? So this error is actually following Gaussian distribution with mean 0, right? So this is the assumption here.
Shall you tell, sir, how the Gaussian distribution is implementing here? I mean, why? What the value is like choosing that one only? And sir, one more thing. What is the sir here? Y and xi, sir, here?
yi is the label for the data point xi.
Okay, sir.
Right. So this is the assumption that noise follows normal distribution with variance sigma square. So it means that your by the label associated with the example xi is actually coming from function w transpose xi. It means it's coming from this line, but some noise added to it, right? Since epsilon follows normal distribution with noise with mean 0 and sigma square, what will be the distribution of this w transpose xi plus sigma epsilon? If x follows normal with mean mu and sigma square, what is the distribution of ax plus b?
It's also normal, right?
It's a normal with mean.
Normal only.
E.
Mean
Forgot.
A mu
yes.
plus variance. A mu plus B, sorry, A mu plus B. And variance?
It's square of it, right?
A square, sigma square.
Yeah.
Right? So if epsilon follows normal 0 sigma square, what is the distribution of this?
So it's a normal.
This is again normal with mean.
Normal. A
W
W transpose xi.
transpose.
And variance?
W transpose x is
Same.
whole square.
Sigma square. Right? So yi given xi follows normal with mean W transpose xi sigma square, right? So we have the distribution of the data given the data distribution of the label given the data point, which follows normal with mean W transpose xi and variance sigma square. Now our task is to estimate this sigma square, this W, right? So can we use MLE here, maximum likelihood estimate? And for maximum
Yes, sir.
likelihood estimate, what we need?
Yes, sir. We can use, but sir, shall you show how this thing implement here? Like we are finding the mean, na sir?
Yeah.
Or WTXI, is this giving a mean?
Okay, let me explain it again. Just give me 1 minute. So this assumption is clear, right? We are making assumption that we are making assumption that your data points are coming from some function y equal to f of x. Your data points, it means the labels given the data points follows some relationship with the feature. It means it's coming from some linear relationship W transpose xi. That is our assumption, but some noise added to it. It means that in that one-dimensional space, if the data points are coming from a line, but some noise added to it. So this is your noise. Okay, so you are data points. Okay, so this is the assumption that the noise follows normal with mean 0 and variance sigma square, right? So since by transpose xi is this and epsilon follows normal 0 sigma square, we can say that W transpose xi plus epsilon follows normal with mean W transpose xi and sigma square, variance sigma square, right? So this follows this distribution, and we have collected some data. Data is your training data set. So can we use MLE to estimate W, right? And what is the procedure of MLE? We find the likelihood, right? Likelihood.
Yeah.
So we have PDF because we have the normal function, right? So we have the data, and for estimation problem, we need some observation, and we always have access to the training data point. So we have data itself, and we know the distribution but we don't know the parameter because we don't know the mean here. We don't know the W, and our task is to estimate this parameter. So we can apply MLE here, and MLE says that first find the likelihood. What is the likelihood? It's the product of PDF function for the given data points, right? So since this by I given xi follows normal distribution, I can write this as this product of the PDF as I'm ignoring the constant term here. So this is gonna be e raised to power sum over by I minus W transpose xi whole square upon 2 sigma square, right? This is the PDF function of normal. Normal is 1 upon root over 2 pi sigma square e raised to power xi minus mu sigma square upon 2 sigma square, right? This is the PDF f of normal. So that's what I've written here and taken the products for each data points. And what is log likelihood? Just take the log of this. This will gonna be this. And how you have to maximize this? Maximize means that you have to take the derivative of this with respect to W and set it to 0. If you do that, you will end up with the problem of maximizing summation over minus by I minus W transpose xi whole square. This is the problem that you have encountered with, or you can even write it as minimizing over summation over by I minus W transpose xi, and that's we already solved. This problem we already solved, right? In the linear regression model. Right? Some rendering issues here. So this is 1. So this problem we have already solved, and we can say that the MLE of W star, assuming what we are assuming, the zero mean noise is the same as linear regression model with what is the loss? Squared loss, right? So MLE again gives the same thing that we have done for the assuming the squared loss. Okay, so that is one reasoning behind why squared loss is the valid choice of the loss function. If you choose any other, if you make any other assumption for the noise, you may end up with some other problem, I mean the other optimization problem in this case. And I'm not sure about the distribution, but some different distribution leads to, I think Laplace is one distribution. If you assume noise to be Laplace, then this leads to the linear regression model with absolute error. Okay, but we all assume that the noise follows normal distribution, and it is equivalent to say that it's the same as linear regression model with the squared loss. Okay. So we only take care of this assumption here. If we change the assumption, that we end up with some different solution for that, right?
How will we solve that MLE then?
We have MLE. We are taking the likelihood here, and we are maximizing the likelihood, right? And maximizing the same as that we have encountered in the initial the optimization problem. This
No, that's
optimization
fine. But how would we solve that MLE?
we have end up with the same optimization problem that we have already solved using gradient descent and normal equation.
I got it that you're saying MLE is the solution to this. So we can go through the MLE method to arrive at the same thing. But how do we arrive, I mean, at that W using MLE?
I mean, you have to solve this optimization problem to get the W star. And how to solve this, we have already seen. We have normal equation method and gradient
Okay, so
descent
we're
method.
just saying that we can
We are
view
just
this
looking at
as an MLE problem as well.
Yeah, we are looking at a different views for the same problem.
Got it.
Okay. Few more slides on kernel regression.
Can I ask a question?
Yes.
So if the noise is not following normal, then will linear regression will be like, is it suitable or not, sir?
Sorry, if noise is not following normal, then
distribution. If it's something else other than normal, then in that case also this solution will be valid linear.
No. Then this optimization problem may be different. And one example I've given here: if noise follows the Laplace equation, Laplace distribution, then this is actually same as the linear regression model with the absolute loss. Okay.
So that y by x will follow normal distribution of the same variance, but WTX, right?
Yeah. So that is the very fundamental property of normal equation, right? If x follows normal with mean, mu, and sigma variance sigma square, then ax plus b, where a and b are the constant, it follows again normal, right? With the mean a mu plus b and variance a square sigma square, right? This is very fundamental property.
Correct. So a mu plus b will be WTX.
Here we are saying that this epsilon follows normal 0 sigma square.
No, that is clear, sir. So now y by x follows what distribution? I know it's normal, but what are the parameters?
So what will be the mean of this?
Mean of this will be mean of WTXI.
So this is, think it as a plus b epsilon.
Correct.
So but if epsilon has mean 0, what will the mean of a plus b epsilon?
Will be the mean of a.
it's just this is a constant A transpose B. Constant
Achha,
but
achha,
unknown constant.
okay. You're treating it as a constant. Okay.
Yeah,
Got it.
constant but unknown constant, right?
Okay.
Sir, why is the mean of noise 0, sir?
But think it as it's coming from here, right? Coming from
Yeah,
this
then
line, that
according
noise
to
here,
that
noise here,
point, different
right?
points, it will be varying.
So on an average, on an average, we can assume that error is 0. So on the
So
line,
there
error will be 0.
you are saying like some points may be above the line which are positive distance, and some points below the line
Yeah.
are
So
negative.
on an average, you can assume the error is
Okay. They will nullify each other. Okay.
But sir, isn't it contradictory, because we are minimizing error? Our objective function itself is, objective is to minimize the error, right? Here we are assuming that error is 0, sir.
No. There we are
noise.
Yeah.
Error
This
and noise is the same thing.
So this error, this is error, right? This is if I look at the distribution of error function. So for this data point, this is the error, some positive, negative error. For this, some positive error. So if I look at the distribution of error function, so it follows some distribution noise with mean 0. On an average, I can assume that error by the data point is 0. I'm not saying that here we have achieved the 0 error. That's not I'm saying. I'm looking at the distribution of the error function, error random variable, you can say.
That's fine, sir. But every error, the mean, if we are taking mean as 0, right? Anyhow, I'm not getting this point, so I don't want to waste others' time.
So GP, if you assume the mean is 0, that doesn't mean anything, right? But because each value could be different, error for each of the projection could be, or each of the projection could be different. They can net be 0, but that doesn't mean we are taking it as 0 and minimizing.
Okay.
Here I'm assuming only the distribution of error function. I'm not saying that I've achieved the 0 error using the model. I'm again landed up in the same solution, right?
Okay.
Here error is this thing.
Okay, sir.
Okay. So should we move for kernel regression, or can we do it in the next session?
I think next session would be better, then we can.
Yeah, next session would be better
absorb
for
all
me.
this. Yeah.
I also
How
think
many
so.
slides? How
Sorry?
many slides in kernel regression?
Sorry,
How many slides in kernel regression?
maybe 4 or 5 slides.
Concept is a bit heavy, Ravi, so it will be better if we cover next class.
Better to cover in the next session. In next session, we will having this we'll start with kernel regression. Then we'll go for that some linear algebra concept, like.
So on Friday, right?
On Friday, 6 to 8.
Friday,
Sir,
6 to 8, is it?
Sir, I have the last question, sir. What is the main aim to? I mean, why we are just approaching the probabilistic method for just finding the regression, sir?
No, it's just the same thing, but different view for that.
Yeah, I think, sir, I felt that like that. It's especially showing that why the least square is best method, like using the normal function.
Yeah, square loss is a better choice that we can conclude from here.
Yes, sir. And sir, any more conclusion from the probabilistic
from
method?
this is not more conclusion, but if you use different distribution, then you will end up with different
Conclusion.
optimization.
Okay, sir. Thank you very much, sir.
Okay.
Good night.
Sir? Just a small request, sir. Could you recommend some good book? Like, why I'm saying for good book, I know there is a list of books available. Our course is, slightly inclined, not slightly, it's becoming too maths heavy, right? So whenever we are referring any video on YouTube and all, so those are not so maths intensive. So if you ask me, it may be that it is a personal problem, so I'm asking this help. Concept wise, it is clear, sir, right? Hello?
Yeah, please go on. Yeah.
Yeah, concept wise, it is clear. The intuitive understanding is clear, like what PCA does, what clustering does, what regression is doing, right? But then so